तू ले ले चलाएंगे, हम यहाँ कर देंगे। वहां कम टाइम लगेगा दादा। आप सोच रहे थे मोतिहारी से जाकर वो सैंपल करिए फिर लाइए, बहुत टाइम लगेगा।
ठीक है, इस पे चर्चा चल रहा है।
हाँ, वही चीज ठीक रहेगा।
नंबर मांगा है, दोनों जगह का नंबर।
Good evening, students. First of all, sorry for the delay in class due to some urgent meeting was held in my institution. So suddenly my principal called one staff council meeting at 4 p.m. which was ended by 5:30. So I am unable to start our class at exactly 5 p.m. today. Today we will discuss the concept and principle of gas chromatography, which is there in your unit 7 of your paper MCH-002 in block 3 of your program postgraduate diploma in analytical chemistry. Before that, I would like to welcome you again to this online platform. This class was organized by IGNOR Regional Center Bhubaneswar. So from in our last previous three classes, we have discussed some methods of separation techniques involved for the separation of components from a mixture, which was followed by your chromatographic general principle, the instrumentation. Then we have discussed yesterday we have discussed, that is in your unit 5 and 6, that involved the discussion on column chromatography, that is liquid chromatography, with planar chromatography, that is nothing but your paper chromatography and thin layer chromatography. So in column chromatography or liquid chromatography, we have two types we have discussed, that is liquid solid chromatography, that is LSC, and liquid chromatography, that is LLC. The liquid solid chromatography based on the principle of adsorption, while liquid chromatography based on the principle of partitioning of the mobile and stationary phase. Then we have discussed planar chromatography, which is generally of two-dimensional, and it is mainly of two types, that is paper chromatography and thin layer chromatography. So in paper chromatography, we have used some cellulose paper like ordinary filter paper, and in thin layer chromatography, we have used thin layer plates, and we have calculated some a retention factor, that is a distance traveled by the individual component divided by distance traveled by the solvent, that is the solvent front. So this is depending upon the retention or the attraction of the different component to the stationary phase or the mobile phase. The retention factor is calculated respectively, and where the retention or the attraction of the component to the stationary phase is more or higher, the retention factor will be less and the separation will be delayed, and the vice versa which also occur. So today we will discuss the next unit, that is nothing but your gas chromatography. So in gas chromatography, just I am sharing my slide. I think my screen is now visible clearly to all of you. Is anyone okay? Akhil, thank you. So In unit 7, we have gas chromatography. So under this separation technique, we have introduction part followed by objective, then some basic concept we have already discussed. What will be the column efficiency, solvent efficiency, followed by instrumentation. What is the mobile phase, that is the carrier gas. What is the stationary phase and the liquid phase, followed by detector. What are the sampling technique, and what are the hazards generally seen in sampling procedure, then followed by some applications. So these are the things are there in our unit, that is the gas chromatography unit. So before going through this PDF, let's have one very simple and understandable PowerPoint presentation which is there for you, that is nothing but your gas chromatography. Just wait. I think some problem is there. Just wait. So let's have some discussion on gas chromatography. In gas chromatography, uh, there is generally the mobile phase is the gas, and the stationary phase it may be solid or liquid. So when the stationary phase is solid, it is uh, it is called as gas solid chromatography, that is GSC. And when the stationary phase is liquid, it is termed as gas liquid chromatography, which is nothing but your GLC. So it is of two types, GSC and GLC. What happened? Wait. It is not working. Just wait. Yes. Yes. I think it is clearly visible. Is it visible, students? Gas chromatography.
Yes, sir, it's visible.
Okay. Thank you. So from its name, it is very clear that here the matter which is to be separated, or the component which is to be separated from a mixture, is under a mechanism that is involved some gaseous phases. So in this gas chromatography mechanism, the gas is there in your mobile phase, and if the stationary phase is solid, it is said to be gas solid chromatography, that is GSC. If the stationary phase is liquid, it is known as GLC, that is gas liquid chromatography. So here, depending upon the stationary phase, the two types of gas chromatography are subdivided. Then this is in your MCH paper 2 and in block 3. So these are some contents in this presentation. Then we have what is gas chromatography. It is also known as gas liquid chromatography, or gas solid chromatography is also there. So in gas chromatography, this technique or this separation method is used for the separation of generally gaseous substances or volatile substances. So the liquid chromatography or thin layer chromatography or paper chromatography, these are used for the separation of liquid samples generally, or the sample in solution state. But the gas chromatography mechanism or the method is used for the separation of generally gaseous samples or volatile substances. Simple and efficient in regards to separation. It is a very simple technique, and it is an efficient one also. When the stationary phase is solid, it is said to be GSC, and when the stationary phase is liquid, it is said to be GLC, that is gas liquid chromatography, and gas solid chromatography is there. And in general, the mobile phase in both the cases, that is GSC and GLC, in both the cases the mobile phase is same, that is the gas. Only the stationary phase differs, that it may be solid or it may be a liquid. If it is liquid, then there will be a supporting solid will be there, like your silica gel or alumina type material. GSC not used because of limited number of stationary phases. So GSC, that is the first one, that is GSC, it is generally not used because for this mechanism or for this separation technique, the type of stationary phase required is limited. So that's why this is generally not used, and generally the GLC is frequently used. For GSC, the mechanism is adsorption mechanism, while in GLC the mechanism is partitioning mechanism. The same thing is there, like your LSC and LHC. In liquid solid chromatography, the mechanism is adsorption. For liquid liquid chromatography, the mechanism is partition. The same is for your GSC. For GSC, it is adsorption. For GLC, it is partition. And this man, that is John Porter Martin, J.P. Martin, he was the father of modern gas chromatography, and he was awarded the Nobel Prize for his development on liquid gas chromatograph in 1950. So he is regarded as the father of gas chromatography. And these are some revolutions in your gas chromatography. That is the first microprocessor controlled gas chromatography is there in 1958, and that is the model 5830 gas chromatography technique. Then which is followed by fast benchtop gas chromatography mass spectroscopy, GCMS is there in 1976, and then which is followed by your fast use silica capillary column. Then in 1984 it is fast electronic pneumatic control. Then fast capillary flow device, that the mu Dian switch, some electronic mechanism is there. So this type of things are advanced things are there, in which is implemented in 2004, and these are some remarkable revolutions in the field of gas chromatography. So gas chromatography is a widely used technique for separation and analysis of gases and volatile substances which are difficult to separate and analyze. So this is widely used, and generally gas liquid chromatography is very much used than gas solid chromatography, because in gas solid chromatography the stationary phase availability of the stationary phase is very much limited. That's why the gas liquid chromatography is frequently used for the separation of your gaseous and volatile substances. In performing gas chromatography separation, the sample is vaporized and injected onto the head of the chromatographic column. The same thing like your liquid chromatography, the sample is injected with the help of microsyringe, um, microsyringe onto the head of the chromatographic column. Illusion is brought about by the flow of inert gas mobile phase. That illusion is needed to detect the separation. In gas chromatography, gas as a moving phase is passed through a column containing solid adsorbent or liquid adsorbent. Thus, adsorption partition is possible. The same thing is there like in liquid chromatography. When the stationary phase is solid, the mechanism involved is adsorption, and when the stationary phase is liquid, the mechanism involved is partition. So based on the stationary phase, it is of two types, that is gas solid chromatography and gas liquid chromatography, GSC and GLC. So in GSC, the mobile phase is gas and the stationary phase is solid. It is very much clear that the first letter is mobile phase and the middle letter is your stationary phase. So that's why the mobile phase is gas and stationary phase is solid. So in GSC, when a carrier gas containing analyte is passed through a column containing solid stationary phase, the analyte get adsorbed on the solid stationary phase, and the separation is due to difference in their adsorptive behavior. The same mechanism applies here for like your liquid chromatography technique. Like depending upon the difference in adsorptive behavior, adsorption to the solid stationary phase, the analyte or the component to be separated, these are separated according to their adsorptivity behavior to the stationary phase. Similarly, in GLC, the mechanism is partitioning. So in GLC, when a carrier gas containing analyte means it is the component of a mixture. So the carrier gas containing the analyte is passed through a column containing liquid stationary phase, and the analyte get distributed themselves between liquid stationary phase and the carrier gas according to their partition coefficient. So depending upon their difference in partition coefficients, in this two liquid, in two that is a mobile phase gas and the stationary phase liquid, there should be there would be a separation of component in a mixture. In GLC, stationary phase is liquid that is retained or coated on the surface of an inert solid. That this is very important. Inert solid like our LLC, liquid chromatography, by adsorption or by chemical bonding. So on this inert solid, it may be your silica gel, alumina, activated charcoal, these things are there. So in inert solid, on the surface of the inert solid, the liquid phase that is used as the stationary phase, the liquid is retained or coated on the surface of the inert solid by the process of adsorption or by chemical bonding. So this is for your GLC. So GLC find much greater application in the analysis of most of the organic compound, while GSC has limited application because semi-permanent retention of active or polar molecule which reduces the available area. So when the GSC is there would be semi-permanent retention of active or polar molecules. Severe tailing of illusion peaks, difficulty in reproducing surface conditions. Surface catalysts also play a restricting role, and at the end we have GSC find application only in the separation and determination of low molecular mass gases like hydrogen sulfide, carbon monoxide, nitrogen oxide, etc. So these are the drawbacks in GSC. So GLC, that is gas liquid chromatography, is widely used for its greater application than GSC. Then we have criteria for compound to be analyzed by gas chromatography. What are the type of compound which is very much suitable for the separation by using gas chromatography? The compound may be volatile or it may be a gaseous sample. It should have a thermostability. The analyte should have a measurable vapor pressure at the temperature employed. So these are the various or probable characteristics of a compound to be analyzed by gas chromatography. What are the advantages of using gas chromatography? It is simple, inexpensive, and generally efficient. The technique has a very high resolution power, and small scale sample is needed for analysis, that is microliter. Sensitivity is very high, that is parts per billion or picogram level. The speed of analysis is too fast. Qualitative and quantitative analysis at a time is possible. The both analysis is possible. That is, qualitative means it is to know what type of component it is, and quantitative means how much it is present or what quantity it is there in the mixture. The area produced under each peak is proportional to the concentration. Therefore, the area increases, that means the concentration is high. For low area, the concentration will be less. How a gas chromatography machine works, that means it is the now the instrumentation part. How the machine works, instrumentation part. So a vaporized sample is injected. This is very clear. For as the chromatography is gas chromatography, that means the sample to be analyzed is in the state of vapor, and it is to be injected by using micro syringe to the chromatography column. The second, the sample moves through the column through the flow of inert gas. So by injecting the sample, so after that, the carrier gas, that is the inert gas, is allowed to flow through the column. So by flowing the gas, what happens? The different components will move according to their attraction or retention to the stationary phase with different flow rate, which separate the component accordingly. The components are recorded as a sequence of peaks as they leave the column. The deals with the stationary and the mobile phase. The same phenomena is supposed to be happen here, and here the liquid phase is gas, that is the inert gas, which pass through the column with passing this inert gas carry the different component with different speeds. The mobile phase is inert gas used as carrier. The stationary phase is liquid coated on solid or a solid coated with column. So these are the mobile and stationary phase used in gas chromatography. Then what is the chromatographic separation mechanism? In the mobile phase, component of the sample are uniquely drawn to the stationary phase and thus enter this phase at different time. So that means in the mobile phase, when the carrier gas or the inert gas is allowed to flow in the column, the different components get separated on the basis of their retention or attraction factor to the stationary phase. The part of the sample separated within the column, this is an important factor is there. The part of the sample are separated within the column. Compounds used at the stationary phase reach the detector at a unique time and produce a series of peaks along a time sequence. That means the components get separated with some time gap or time period interval and produces a series of peaks. The peak can then be read and analyzed by a forensic scientist to determine the exact component of the mixture. Retention time is determined by each component reaching the detector at a characteristic time. That means when the different components separated and detected at the detector end with unique time, and this will be detected qualitatively as well as quantitatively. So this is the instrumentation part. So in instrumentation part, we have the carrier gas supply or tank here, which will supply the carrier gas. That is the mobile phase. Okay. So through this
Hello,
pressure regulator,
sir. There is
yes.
there is no screen.
No screen.
We cannot see any screen.
Is it visible, students?
No, no screen.
Yes, visible, sir.
We could not find.
Yes, visual, sir.
So,
Yes, sir,
mm,
visible.
okay, okay. So someone is facing some problem. I think you may log out, then again log in, then again your problem it would be solved. Okay. So the student which is facing problem, I am suggesting you to log out, then again log in, then you may see the screen clearly. Okay. Is it visible, students?
Yes, sir.
Okay,
Yes, sir.
thank you, thank
Yes,
you,
sir.
thank you. Okay, thank you. So here in the instrumentation of your gas chromatographic apparatus or the machine or instrument, you may say, there is a carrier gas supply is there, which is nothing but your mobile phase. So with the help of this pressure regulator, this carrier gas will flow in this pipeline. So there is pressure gauge is there to adjust or to regulate the pressure. So there is a flow meter is there, that is flow splitter is also there, which through which the carrier gas will flow. And this is the column, that is the gas column. This is a coil like structure. This is the column, actual column which is there in your gas chromatogram. This is the sample injection port. So this is just a cap is there or knob is there. So we will open the cap like the cap on a bottle, and we will inject the sample through the by using the micro syringe. And by injecting the sample, the injected sample will flow in this column, the coiled structure column. And with the flow of this carrier gas, what happen, the different components will separated according to their attraction or retention to the stationary phase. And finally the different components will separated on the basis of their retention factor by through this detector. And we have a computer screen here which will show or which will display different peaks on the basis of the different component, step by step or one by one, they are once they are starting to separate. So there is carrier gas tank, this one, flow regulator, these regulators are there, the pressure regulator, pressure goes there, sample injection system is this one, sample injection port, column and stationary phase, this is the stationary phase, and this is the column is there, and last one is the detector. So this is a broad idea of your gas chromatography technique. So this is the modern instrument of your gas chromatography is there. And here this is the sample chamber or sample injection port. Here the cap is there, that is the sample cap. You just put out this cap, inject the sample, then again close this knob and run your machine. Then after few 1 to 2 minutes or 5 minutes, what happen, your computer screen will display different peaks. And you will analyze the different peaks, and you will able to know what kind of component is there, and in how much quantity they are present in the sample. And also this gas chromatography mass spectroscopy, that is GCMS in short, gas chromatography mass spectroscopy. This GCMS instrument is used in satellites, that is uh, our Chandrayaan 3, Chandrayaan 2, Aditya, that one there, in Aryabhata, these satellites, this GCMS instrument or spectroscopy is there to detect the unknown component present in the moon or in the Mars, Mangalyaan or Chandrayaan is there. So to detect different components or the element present in their atmosphere or in their soil, for the advanced determination, this GCMS instrument is very much helpful. So what are the carrier gases? Carrier gas system means it is the mobile phase. The main purpose of carrier gas is to transport sample component through the column. So the mobile phase is to transport the sample component. It will flow, it will help to flow the different component of a mixture through the column. It determines the efficiency of the column, the time of analysis and sensitivity of the given detector. So it will determine the efficiency of the column, the time of analysis and the sensitivity of the detector. Factors which are affecting or which are responsible to detect or to select a carrier gas, the carrier gas must be chemically inert. That component which we are wish to separate, that component or that mixture composition should not be react with the carrier gas or the mobile phase. So the carrier gas or the mobile phase must be chemically inert. They should be in pure and stable form. That the carrier gas must have the stable isotope. If I use the carrier gas as a nitrogen gas, that it should be N714. N715 is radioactive. So the isotope which I am using as the carrier gas, this must be in their stable and pure form. There should be free from moisture. This is very simple, and should give best column performance consistent with desired speed of analysis. So these are written or these are displayed on their catalogs for different carrier gases. Suitable for detector used, inexpensive, readily available, safe in handling. So these are some characteristics before selecting a carrier gas for a specific purpose of separating different components in a mixture. So there are makeup gases. Flow rate required for most detector is 30 to 40 milliliter per minute. So this is the minimum speed of the carrier gas to be flow through the column. That is 30 to 40 milliliter per minute flow or flow rate should be there for separation. Mobile phases are carrier gases which is used in gas chromatography. So just see, here there is helium as the carrier gas, general carrier gas or makeup gas, and this is expensive because this is an inert gas, and their availability is very less. So that's why it is very expensive. Nitrogen, which is cheaply available, so this is very cheap, but not good for capillary column as it gives long run time. Gas, generally carrier gas or makeup gas, it can be used. So oxygen, this is combustion gas for your flame integration, flame ionization detector, FID, flame ionization detector. So normally not used. Oxygen. Argon, this is thermally conductivity detector, TCD, thermal conductivity detector. So argon, there is where there is application of heat is there, for that separation argon gas is used. Hydrogen, carrier gas, capillary column and combustion gas for flame ionization detector. Then we have ordinary air. It would be FID, that is flame ionization detector, NPD, that is nitrogen phosphorus detector, or as well as FPD, that is fluorine phosphorus detector. Then argon plus methane, this is makeup gas, that is flow rate of 30 to 40 milliliter per minute is there. Also used as the carrier gas for your ECD, that is electronic conductivity detector, I think. I don't know what is ECD. electron capture detector. So this is very much used in your electron capture detector. Okay. 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 So pressure regulator, gauges, and flow meter are required to control the flow rate of carrier gas. This instrumentation parts are there, different parts of your GC chromatography instrument. Inlet pressure usually ranges from 10 to 50 psi, uh, greater than the room temp pressure, which leads to flow rate of 20 to 25 to 150 milliliter per minute for packed column, and 1 to 25 milliliter per minute with open tubular column, capillary column. So column again of two types, the packed column and open tubular column, we will discuss later. So how to measure the flow rate? It is to maintain the optimum operating condition for analysis and also to reproduce this condition when necessary. So the flow rate should be maintained or measured to optimize the operating condition and to reproduce the condition again. A device commonly employed to measure flow rate. The rotameter is there, which is used for the measurement of the flow rate. It is a fixed in line and with carrier gas on the column head. This device is not as accurate as the simple soap bubble meter is there. Okay, this is a soap bubble meter is there, which is used for to detect the flow rate. So it is located at the end of the column. This one, this is the soap solution, rubber valve is there, gas inlet is there. This is the soap bubble. So by using this meter, we can measure the flow rate. So this is not needed for your examination point of view. The time is then converted into volumetric flow rate by the equation. Volumetric flow rate is the distance between graduation A and B by time taken. So A to B, what is the distance? That will be divided by the what time it take, that will be the rate, because we know that speed equal to distance per time. So here rate in terms of speed, it is equal to distance, total distance traveled divided by total time taken. So by linear flow velocity equation, we have F equal to u o, that is for your UOA, and UO into these equations are there. Just try to remember these equations, okay? Where F is your volumetric flow rate in liter per minute, sorry, milliliter per minute. UO is the linear flow velocity. A is the area of the tube, and epsilon is the fraction of the total volume of the column available for the gas. And the first one is for your open tubular column, and second one is for your packed column. So there are two types of columns are there, and F stands for your flow rate. This is sample injection system. This is the known as the micro syringes. Column efficiency requires that sample must be suitable size and be introduced as a plug of vapor. Slow injection or oversized sample cause band spreading and poor resolution. So these things are there. Slow injection or oversized sample can cause band spreading. That means when we get the peak, the band is spreading, the broadening of the band, band is there, so which has poor resolution. Then calibrated micro syringes, this type of syringes which are very much scientifically calibrated, are used to inject liquid sample through a rubber or silicone diaphragm or septum into a heated sample port located at the head of the column. So always the sample is injected into the column through the head. Okay, by using these micro syringes, which are very much scientifically calculated, and by using a rubber or silicone diaphragm. The sample port is ordinarily kept as 50 degrees centigrade, greater than the boiling point of the least volatile component of the sample. Ordinary packed column, this is of 0.1 ultraliter to 20 UL. Capillary column is smaller by a fraction of 10, 100 or more. A sample splitter is always needed with capillary column. Reproducible sample size for both liquid and gas are obtained by means of rotary sample value. So this is your sample in, and when the analysis is done through here, that means this is a sample in, sample is injected, this will be your sample characterization, then the remaining sample will flow through this port and it will be sample out is there. Okay, and there must be an illusion is there. So this is your sample size. So solid samples are introduced as solution or sealed into the thin walled vials that can be inserted at the head of the column or punctured or crossed from outside. So by vials or your solid samples are introduced as solution for their analysis. So now the column, which is the stationary phase. Column is the stationary phase. So the column, it is generally of two types, there is packed column and open tubular column. This packed column and open tubular column is also known as capillary column. So packed column of length is 1.5 to 10 meter, that is and capillary column is 100 to 10 to 100 meter. So capillary column is generally of longer or very much large in size by length to your packed column. Construction of it is constructed by stainless steel, glass, or fused silica or Teflon to fit into an oven for thermostating. They are usually formed into coils having diameter of 10 to 30 centimeters. So as we see that in our instrumentation slide, the stationary phase is nothing but a coil-like structure. So here the dimension is there. It is of diameter 10 to 30 centimeters. The first type, which is packed column, it has the inside diameter of 2 to 4 millimeter. These tubes are densely packed with an uniform, finely divided packing material or solid supporting materials, that is diatomaceous earth glass bead, that is then coated with a thin layer of stationary liquid phase is there. Solid support, what are the solid support? Now purpose, it serves to hold the liquid stationary phase in place so that as large of surface area as have possible is exposed to the mobile phase. Example is naturally occurring, it is your diatomaceous earth or glass beads. So these are the solid supporting materials which are used in the stationary phase in a GSC. Ideal characteristics of your in your packed column selection, it should be small, uniform and spherical, good mechanical strength, specific surface area of at least 1 meter square per gram, inert at elevated temperature, then uniform wettability. Support material are often treated chemically with dimethyl chlorosilane. The HETP is proportional to average particle diameter, so the smallest possible particles should be preferred in terms of column efficiency. Particle size is 60 to 100 mesh, that is the size of the silica gel, 250 to 170 ultrameter. Then we have some open tubular capillary column is there. Its inert diameter is 1 millimeter. It is again of two types, that is wall coated and support coated. If it is wall coated, it is WCOT, and if it is support coated, it is SCOT, Scott. And for WCOT, they are simply capillary tubes. They are simply capillary tubes coated with a thin layer of stationary phases. So WCOT is nothing but the capillary tube coated with it is coated with a thin layer of the stationary phases. WCOT columns are constructed with stainless steel, aluminum, copper, plastic, glass, etc. The column in WCOT is treated with gaseous HCl, strong aqueous HCl, or potassium hydrogen fluoride to give a rough surface which bonds the stationary phase more tightly. So these acids or your potassium hydrogen fluoride like chemicals are used to make the surface of your WCOT, that a wall coated with open tubular packing, rough, so that the binding to the stationary phase will be more tightly. The it is your SCOT, that is supported coated open tubular packaging. The inner surface of the capillary is lined with a thin film of 30 of a supporting material, so that the diatomaceous earth on which stationary phase is coated. Scott columns are less efficient than WCOT but have a higher sample capacity which enables them to use without a sample splitter. The recent is advancement in the capillary column is fused silica, that is FSOT. They are drawn from a specially purified silica that contain minimal amount of metal oxide. The see here, this is a wall coated, this is your supported coated. Okay, so this is wall coated, this one, and in SCOT the surfaces becomes rough, so that the adherence or the binding will be more strong. Liquid stationary phases. If the stationary phase is liquid, so it would be supported by a supporting material, that may be your silica gel or alumina or charcoal cavity like inert materials are there. So these liquid stationary phases must have low volatility. That means it should be highly adsorbed on your supporting stationary phase. It is ideally the boiling point of the liquid stationary phase should be at least 100 degrees centigrade higher than the maximum operating temperature of the column. So if if the liquid stationary phase is more volatile or having volatility property is more, then on application of some temperature or heat to the column, the liquid stationary phase will be escape. So that will hamper the analysis. So the liquid stationary phase must be carefully chosen, um, and it should have low volatility so that it cannot be escaped from the surface of the supporting stationary phase to access the mechanism or the gas chromatography procedure effectively. It should be thermally stable and it should be chemically inert. The proper choice of stationary phase is often crucial to the success of the separation. This is very important. For separation by chromatography testing, the stationary phase should be carefully chosen. Some important fact of stationary phase: the retention time for an analyte or a component on a column depends on its distribution constant, which is nothing but the retention or the attraction of the component to the stationary phase, also to the mobile phase, which in turn is related to chemical nature of the liquid stationary phase. To separate various sample component, the distribution constant must be sufficiently different to accomplish a clean separation. It is very important. The distribution constant, that one component is separated from the remaining components distinctively, that must be a distribution constant should be sufficiently different. That is, the separation must be very clear, that one component do not match with the other components, which will give a clean separation. At the same time, This constant must not be extremely large or extremely small. This distribution constant. To have a reasonable residence time in the column, an analyte must show some degree of compatibility with the stationary phase. Principle involved like dissolves like, that is polar solvent or polar component will like the polar stationary phase, the non-polar component will like the non-polar stationary phase. So like dissolves like, this is the standard principle which we are already known. So that's why the component as well as the stationary phase must be like or must be same. Generally, the polarity of the stationary phase should match with that of the sample component. When the match is good, the order of illusion is determined by the boiling point of the element. So these are some examples of a liquid stationary phases used in GLC, that is in gas liquid chromatography. Then this is the first example is polydimethyl siloxane. The trade name is this one. The temperature it can sustain is 350 degrees centigrade, and the purpose is it is used in non-polar phases, hydrocarbon, polynuclear aromatic steroid. These are the applications. Then we have 5% phenyl polydimethyl siloxane having the trade name AC52OV3. Again the 350, and the applications are in fatty acid methyl esters and etc. Then we have 50%. Then we have 50% trifluoropropyl polydimethyl siloxane polythene glycol. Its trade name is Carbowax 20M. 50% cyanopropyl polydimethyl siloxane, that is OV275 is there, having the maximum temperature of 240 degrees centigrade, and these are the applications. Then this is siloxane. This is the repeating unit, that is silicon. The first silicon in siloxane is bonded to three alkyl groups RRR, and the fourth bond with the oxygen, and that oxygen is also linked to the second silicon atom with the two alkyl groups with another oxygen. So the repeating unit is this one, that is SiORR. This linkage will repeat it again and again to give high molecular weight polydimethyl siloxane. The repeating unit is this one, this bracket. This is a repeating unit. So the small n is here. It may be 2, it may be 3, it may be 4, and it may be higher number. So the important part of a GC is the detector part also. So what are the characteristics of a good or ideal detector? It must be adequately sensitivity. That means it should have a good sensitive power. Generally, detector should detect the solute in picogram quantities, that is 10 to the minus to 12, minus 12 pico. Good stability and reproducibility, a linear response to solute that extend over several order of magnitude, a linear response to solute, that is the component that extend over several order of magnitude, a temperature range from room temperature to at least 400 degrees centigrade, a short response time that is independent of flow rate, high reliability and ease of use, similarity in response toward all solute, or alternatively a highly predictable and selective response towards one or more classes of solute, and finally there should be non-destructive of sample is there. Then the type of detector, one type that is thermal conductivity detector is there, which is also known as catharometer or hot wire detector. This is the principle, that is rate of loss of heat from a body depends upon the thermal conductivity of the surrounding gas, which in turn is a function of its composition. It is again the same cycle continues. A thermal conductivity detector. Thus, the rate of loss of heat is related to composition of the surrounding gas. It is very much same as your law of conservation of mass. Then your thermal conductivity detector TCD. This is made up of the fine platinum gold or tungsten, where TCD thermistors are made up of oxide of manganese, cobalt, or nickel, to which some trace elements are added. The advantage of these TCD filaments or TCD thermistors are their simple, large linear dynamic range. It gives general response to both organic and inorganic species. These are very much non-destructive, which permits collection of solute after detection. And these detectors have low sensitivity. The relative thermal conductivity of some different compounds are given here. The CCl4 has 0.05 ohm inverse, and benzene has 0.11, and so on. Hydrogen is 1.28, helium 1.0, nitrogen 0.17, methanol 0.13. This type of relative thermal conductivity data are there. Then flame ionization detector, that is FID. The first one is TCD. This is FID, flame ionization detector. Flame ionization detector, it is not concentration sensitive, but it is rather mass sensitive is there. That is, it is given response proportional to total mass of component entering the detector, and therefore independent of carrier gas flow rate. So this FID, that is flame ionization detector, it is not concentration dependent, it is mass dependent, or it sends how much quantity of mass of the component present in the given mixture. Then electron capture detector, that is ECD, it responds to only those compounds which molecule have an affinity for electron. Example, halogen containing organic compounds such as pesticide and polychlorinated biphenyl, peroxides, quinones, and nitro group containing compounds. On the other side, it responds very little to compounds such as hydrocarbon, alcohol, and amine. So where the compound has or have some affinity towards electron, that means the ionic species which has the affinity for electron are very easily detected by using the electron detector capture detector. And this is an example or schematic diagram of your ECD, electron capture detector. It is made up of Teflon, and it would have cathode and anode type. That is, cathode and anode is there. So anode is positive charge, cathode is negative charge here. This is tritium foil or nickel 63. It is your filament is used here. And when we use this detector, then electron capture component are easily detected. Important cathode gas chromatography detector, the TCD, most compound, the linear dynamic range, and minimum detectable quantity. These are given here in gram. Flame ionization, most organic compounds. Then thermionic, it is NPFID, that means phosphorus, nitrogen, and this is sulfur, hydrogen, halogen compounds. Then again ECD, flame photometric, and photoionization, that is PID. So these applications are there with some linear dynamic range, always minimum detectable quantity. What is the theory of your gas chromatography? The theory is retention time, which is abbreviated as TR, and this is the time gap between sample injected and appearance of the chromatographic peak for a particular analyte is called retention time. That means at what time you inject your sample and at what time you see the peak on your computer screen or in your recorder. So the time gap or the time interval is known as the retention time. So here it is written, the retention time is nothing but your Tm plus Ts, where Tm is the, where Ts is the sample injection, I think, and Tm is the your for your analysis. That is the, this is the time gap Tm. So used for date time or void time. So this is the C, this is the starting time, and this is the first peak, that is Tm, and this is the second peak, mean peak, that is Ts, and the overall is your Tr. Okay, that is from 0 time to the second peak. This is the date time. Provide a measure of the average rate of migration of the mobile page is an important parameter in identifying analyte peak. All components spend time Tm in the mobile page. Okay, this is the time spent in mobile page, and this is the time spent in stationary page. That's why it is Ts. So the summation of your Tm and Ts, that is time spent in mobile page and time spent in stationary page, the summation of these two will be your retention time, that is Tr. And depending upon the Tr, you will have separation of the different component in a mixture. Now for resolution is the degree of separation between two adjacent peaks. Degree of separation between two adjacent peaks. This is one peak and this is second peak, so this is the resolution. The distance between two adjacent peaks divided by mean of the two width. Mean of the two width. That means it is the distance is 2d, r equal to 2d divided by tw1 plus tw2. So d is the distance traveled by the two peak, and tw1 is the width of the first peak. This is the width, and this is the width of the second peak. If r is 1.5, the baseline separation is 99.7% resolution is achieved. So these are some computer characterization. The resolution of chromatographic peak is dependent on two parameters, that is column efficiency and solvent efficiency. So the chromatographic peak resolution depend on two parameters, column efficiency and solvent efficiency. Column efficiency is nothing but your stationary phase, and solvent efficiency is nothing but your mobile phase. So column efficiency band or column efficiency, chromatographic bands are usually Gaussian curve or normal error curve, and the efficiency of the column is reflected in the breadth of the chromatographic peak. Hence, column efficiency is H, that is defined as sigma square by L, where sigma is the standard deviation, sigma square is the variance, and L is the length of the column. So what is standard deviation, what is variance? These things you have already studied or already taught in your paper 1 MCH-001 paper, which I will not repeat here. So just remember, column efficiency is abbreviated as H, and it is the variance divided by length of the column. Variance is your square of your standard deviation. The factor affecting column efficiency, it is plate theory and rate theory. Two types of theories are there. These things are there or not in your PDF? I think these things are not there. This open tubular, this type of things are there. Stationary support, liquid phases already done. These are some examples. Then this one, these are the liquid phase percentage, column temperature, detector already discussed. Then we have detector sensitivity, detector response. Then we have already discussed these things: thermal conductivity, flame ionization, flame capture, helium ionization, and flame emission. These things already discussed. Then we have, in a helium ionization detector is not in my slide. It is a universal detector. Photo ionization is there. Sensitivity to fractional parts per million. The helium ionization detector is a universal detector, except of course It will not sense helium. It will not sense helium. The combination of tritium beta radiation and high field gradient raise the helium to metastable state with an ionization potential of this 19.8 electron volt. All the solutes having a lower ionization potential will be ionized, giving rise to a positive signal. The helium ionization detector was developed for the ultra trace analysis for permanent gases. So just go through these things, and then at the end we have sampling technique. So sampling technique is there or not? It is not needed for your examination or your PDF point of view. So I am just skipping. I just switch over to the sampling technique. No, this is not there. Yes. So the sampling process involves the several steps. The removal of an alicot from a bulk quantity, which is the representative of that bulk. This is that means the mixture should be uniformly distributed, such that our sample must be a representative of our mixture. If necessary, alternation of the physical state of the sample so that it can be manipulated, transportation of the lab for analysis, storage prior to analysis, introduction of the sample into the GC unit for analysis. So these are the some sampling procedure. Hazards in sampling: in the sampling, handling, and storage of the gaseous and volatile materials. There, there are some hazards involved, and due precautions should be taken. The analyst must, as a general rule, try to obtain a prior knowledge of the material which is expected to be analyzed. The analyst must wear adequate protective clothing during sampling. Adequate antidotes, etc., must be kept ready before proceeding for sampling work. No naked flames should be allowed near a sampling area. If the sample is known to contain inflammable components, many gas or vapors may be toxic. Pressure changes may release excessive quantities of gases. Spontaneous ignition of inflammable gases may occur. Sudden vaporization of liquefied gas may take place. Volatile and inflammable liquids may pose sufficient danger to a careless analyst. Using a face mask, goggles during sampling is highly recommended. That means before sampling, on sampling, handling, storage, in each and every step of sampling, precaution must be taken care of to our physical as well as our mental state. That we should use gloves, wear goggles, surface mask, should be we should avoid, or we should be very careful towards toxic materials, inflammable components. These things are there. Introduction of sample into the GC unit. So it must have sample size sense of sample size, sense of injection system, and sense of sample injection port. So these things are there. So in sample size, the sample volume may vary depending upon the amount or rate of vaporization of the sample in the sample port in the case of liquid. In case of gases, it is common practice to vary the amount of sample by introducing different volume at a constant pressure. The sample size will obviously be different related to the kind of solute stationary phase interaction and consequently to the shape of the final chromatographic peak obtained. And this is the injection system. That is, the injection port is here, the head of the column. that is the head of the stationary phase. So the injection is done with the help of micro syringes using a septum. So various kind of injection systems have been incorporated in commercial gas chromatography units. That there would be direct injection, that the sample is injected directly, split injection, splitless injection, so phase by phase, solid injection, that means the sample is in solid phase, that is moving needle. In case the solvent is evaporated before injection, resulting in improved separation of fast eluting component. Just read these things on column injection, valve injection, thermal desorption, cold trap injection. There is a purge or trap injection is there. Then sample injection port. This is the micro series or sample series, which has some needle, plugner, sample is here. So like a ordinary syringe, this is just a micro syringes, which is of capacity of 5 microliter or 10 microliter of capacity, but depending upon your sample size, you are supposed to use this type of syringes. A sample injection in a liquid on packed column. This is a packed column, glass hole. So this is the carrier gas injected. This is the septum. That is the that is your this is the syringe which is introduced in the stationary phase. That is the column, and the sample or the mixture is injected. And here gas sampling valve is there. Let's go through these things. Carrier gas, sample in, activator, sample loop is there. Then some application, that is identification of compound, qualitative analysis, then also quantitative analysis there, and some examples of application is also there. In qualitative analysis, we are able to know what type of component is present by analyzing different peaks which are obtained in the recorder after one GC run. Then after the quantitative analysis, we have area normalization method is there, that on the basis of that area, we are able to calculate the concentration or the by weight determination of the component present in the given sample. Internal standardization method is there, as a how to standardize internally. In this method, a known amount of sample and standard are mixed and chromatographed. That means the sample is known, and once standard is used, both are mixed and chromatography is run. So by this method, the standard must be a compound which is well separated from all component. The standard must not react with any component. It should yield a symmetrical chromatographic peak. It must be chemically similar, and to the unknown, it should have concentration comparable to the component of interest. So the standard which is mixed to the sample must have these characteristics. So there is comparison method, that is between the standard and the sample used simultaneously. Some examples of application is bacterial identification, environmental analysis. We have water analysis, air analysis. Then we have clinical and toxicological analysis, forensic toxicology, and after that it is summary. So in environmental, we have water analysis. The organic pollutants in water are concentrated from water sample by solvent extraction or by purge or trap technique. The volatile pollutants are analyzed on 80 to 100 mils carbopack, carbon of 0.2%, carbowax of 1500 column. So just go through these things. So this is all about your gas chromatography in general. So this is a very long unit or long chapter in your paper MCH-002, that is unit 7. So we may have some questions or anything anyone wish to ask or anyone wish to share? So this is open for 5 minutes. So is there any question or anything? Janardhan. Janardhan Iyer.
Hello, sir. Good morning, sir.
Yes,
Good,
yes,
good
yes.
evening,
Good,
sir.
good evening. Good evening.
Sir, what is the use of the SEPTA, sir? You just to tell about the SEPTA, the gas
Oh, septum.
chromatography
Yes,
SEPTA.
septum, septum. The septum is
Septum, yes,
nothing
sir.
but, yes, septum is nothing but a rubber-like structure. Okay.
Okay,
So
okay,
this is just to cover the container, which is wait, septum in chemical analysis. Yes, this is known as septum. So
Acha,
just
okay,
the container which is used for the chemical reaction or the separation, the septum is
okay,
to cover the mouth of that container to
acha,
separate it from the impurities in the environment. So when
okay,
we use the
okay,
syringe, what happened? The mouth must be open. So in that open mouth, impurities may come in contact with our sample or the stationary
okay,
or the liquid phase. So that's why these septums are used, and these are made up of rubber, that is
okay,
natural or artificial rubber or synthetic rubber.
okay,
And through this
okay,
rubber, the micro syringes are in, and we will
acha.
able to add the sample to the stationary phase.
Sir, one of the questions, sir. Sir,
Yes, yes.
the mostly common used the detector. What is the type of the detector present in the gas chromatography, sir?
So this
Detector.
detector, for various detectors, what happened for different components, we are
Okay,
predicting that this type of component is there in my mixture. So on the basis of
okay,
my prediction, I have to detect or I have to select the which type of detector I will use, which is best for
acha.
my sample. So this
Okay,
is
okay,
also
okay, sir. Okay,
this is what is say, there is a chart is there for this detector.
acha.
These components is easily detected. So on the basis of that, I
Okay,
will use the detector. That is, it may be FID, it may be TCD, it may be
ha ha.
HID.
Yes, yes, yes,
So depending on
yes,
that.
yes.
Okay.
Okay, 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 sir. Thank you, sir. Thank
Okay.
you.
So anyone? So student, we may have let's have some 5 minute break. I just take some water, and after that I will take Unit 8, that is high performance liquid chromatography in general, and let's have some break of 5 minutes. So thank you. Am I audible, students?
Yes, sir.
Okay, thank you. I think my screen is shared now.
Yes, sir.
Okay, okay, thank you. So we have successfully completed unit up to unit 7, and today we will have some discussion on high performance liquid chromatography. In short, it is HPLC, and which is recommend or it is accepted as an advanced separation technique in terms of chromatography is concerned. So high performance liquid chromatography is based on the principle of your liquid chromatography, that is nothing but your LSC and LLC. In LSC, that is liquid solid chromatography, where the mobile phase is liquid and stationary phase is solid, and which is based on the principle of adsorption, while the liquid chromatography is based on the principle of partitioning, that is liquid as the mobile phase and liquid as the solid phase. But in solid phase, the liquid is coated on a supporting solid phase like silica gel, alumina, charcoal, that is activated charcoal, etc. So this high performance liquid chromatography is an advanced version of that liquid chromatography, and in this unit we have some objective principle instrumentation, and followed by the optimization of separation, what are the advantages, and finally the comparison with gas chromatography, as well as some applications. These things are there, and in the introduction part I just skip this one, just read out. And what are the objectives? In this unit we will able to understood what do we mean by HPLC, and what is the difference between classical liquid chromatography and HPLC. Discuss basic principle and working mechanism. Describe various components of instrumentation including stationary and mobile phases. It describes characteristics of stationary phases in various modes including bonded phases. Know the solvent delivery system, characteristics of mobile phase and illusion gradient. Understand various detector used in HPLC like your gas chromatography. Learn about versatility and advantages. Know about various interfaces while using mass spectroscopy as detector. Learn about application of HPLC for various applications. So I have just have one PDF on HPLC. Let's have a look on this PPT in the form of PDF. So this is introduction to high performance liquid chromatography, and this is introduction to liquid chromatography and HPLC chem station. This is just a supplier of this instrument. So this is their catalog, that is Agilent technology. This is the supplier. Then what is HPLC? It is nothing but a high performance liquid chromatography. It has also been referred to as high pressure liquid chromatography before, but it is renamed as high performance due to its advancement and precision. This is highly uh, preferred nowadays. So HPLC has been around about 35 years of used, and it is the largest separation taking to be used so far. The history of HPLC beginning with 60s, the HPLC has high pressure liquid chromatography. End of the 70, improvement of the column material. 70s means 1970. In the year, improvement of the column material and instrumentation, high performance liquid chromatography. Since beginning of the 80s, it is boom in HPLC started. In 2006, The new term popped up like UPLC, RRLC, these things are there. Ultra filter liquid chromatography, and what is the from these things I don't know. This is from Wikipedia. SPLC, which is referred to as high performance liquid chromatography, is a technical analytical chemistry used to separate a component in a mixture, identify each component, and to quantify each component simultaneously. This is qualitative as well as quantitative. It relies on pumps to pass a pressurized liquid solvent containing the sample mixture through a column filled with a solid adsorbent material. That means here the stationary phase is solid and the mobile phase is liquid, and here one unique thing is there, that is the solvent or the liquid phase is passed with pressurized liquid. That means it is forcefully passed. So that's why the analysis becomes very easy and it is not time consuming. It requires lesser time that than our traditional or classical liquid chromatography is supposed to take in. Each component in the sample interacts slightly differently with the adsorbent material, causing different flow rate for the different component and leading to the separation of the component as they flow out the column. So this is again on the basis of your adsorption phenomena. SPLC is a separation technique that involve the injection of a small volume of the liquid sample. So very small amount of the sample is required. It is into a tube packed with tiny particles in diameter called the stationary phase. It is just a small tube packed with tiny particles of our stationary phase, that is the silica gel. Maybe the silica gel or the alumina or the activated charcoal is there. This is maybe taken as the stationary phase of the diameter of 3 to 5 micron, very thin, and where individual component of the sample has moved down the packed tube with the liquid forced through the column by high pressure. That means the mixture or the is injected into the liquid or the solvent is forced through the column with very high pressure, that is forcefully, with the help of a pump. These components are separated from one another by column packing that involve various chemical and physical interaction between their molecule and their packing particles. That means they will adhere or adsorb to the surface of the adsorbent, that is the stationary phase, with different interactions, and through this difference in their interaction to the stationary phase, the different components are separated one by one depending upon the retention factor. Again the same thing comes. These separated components are detected at the exit of the tube, that is the column, exit of the tube or last or the bottom point of the tube, where the detector is connected, and with that detector the recorder will record or show the peak of that component. So this is an output from this detector is called liquid chromatogram. In principle, the liquid chromatography and high performance liquid chromatography work the same way. Just wait. ମୁଁ କ୍ଲାସ୍ ନଉଛି ପରେ ଆସିବୁ ପାଠ ପଢୁଛି ଆସିଲେ works the same way except the speed, because here the mobile phase, that is the liquid or the solvent which is introduced into the column, that is stationary phase, but the difference is the pressure or the force with which it is injected or with it is introduced into the chamber or the column. So the speed efficiency also enhances, sensitivity is more because advanced detectors are used, and the separation of operation SPLC, it is vastly superior than classical or traditional liquid chromatography. This is the comparison of GC with your HPLC. This comparison is polarity. It is hydrophilic and hydrophobic. Hydrophilic means it is becomes polarity increases, here polarity decreases, and here volatility decreases, sorry, it is increases, and here it is decreases, non-polar, that is a non-volatile, sorry, non-volatile. So this is volatile gas phase, non-volatile liquid phase. So we have the borderline here where the samples like this, which are very much polar to non-polar, and it is also polar to non-polar, volatile to non-volatile things are there. This will be separated according to their GC and HPLC technique. Am I audible, students? Am I audible?
Yes, sir.
Okay, thank you. So we have five major components in our high performance liquid chromatography instrument. The major component number one is pump, which is there to introduce the solvent or the liquid or the mobile phase to the column, that is the stationary phase, with a high speed or specific flow rate is there. The role of the pump is to force a liquid through the liquid chromatograph at a specific flow rate that is expressed in milliliter per minute. Normal flow rate is 1 to 2 milliliter per minute, and a typical pump can reach pressure up to the range of 6000 to 900 psi or 400 to 600 bar. During the chromatographic experiment, a pump can deliver a constant mobile phase composition that is isocratic. If the composition is same, it is known as isocratic, or an increasing mobile phase composition of gradient. So this pump is used mostly or generally to enhance or to have a specific flow rate of the liquid or the mobile phase to be introduced into the stationary phase. The injector, that is the sampling, that is the injector. The injector serves to introduce the liquid sample. Just see here, number one is the pump, that means pump is here. Number two is here, this is the injector. So injector is to introduce the sample into the flow stream of the mobile phase. Typical sample volume are 5 to 20 microliter. The injector must also able to withstand the high pressure of the liquid system. An auto sampler is the automatic version for when the user has many samples to analyze or when manual injection is not practicable. So the number two part component of this SPLC is the injector part, which is used to introduce the sample into the chamber or the column. Then we have column part. This is the number three. This is the column part. That means it is the stationary phase. It is the column. Consider the heart of the chromatograph. The column stationary phase separate the sample component of the interest using various physical and chemical parameters. Physical parameter means it is the adsorption phenomena, and chemical parameter means it is the chemical bonding formation. That means two types of things may occur between the solute, that is the different component of the mixture, with the surface of the stationary phase. That means on the surface of the adsorbent, that is the stationary phase, the component or the solute which is to be separated may have the principle of adsorption is there, or may have the principle of chemical bonding is there. The small particle inside the column are what cause the high back pressure at normal flow rates. The pump must push hard to move the mobile phase through the column, and this resistance causes high pressure within the chromatograph. That means the pump plays a major role, which put or introduced the mobile phase into the column forcefully or have high flow rate, so that the separation becomes easier. Detector, the detector can see the individual molecules that come out from the column with the help of illusion. So a detector serves to measure the amount of those molecules so that the chemist can quantitatively analyze the sample component. The detector provide an output to a recorder or computer that result in the liquid chromatograph. That means a recorder is connected with this HPLC instrument. So through this recorder, we are able to see different graphs or different plots or peaks of different components separated from that mixture. Computer, frequently called the data system. The computer not only control all the modules of the HPLC, but also it takes the signal from the detector and uses it to determine the time of the illusion. That is the retention time. So here the retention time is nothing but your time taken in mobile phase plus time taken in the stationary phase of the sample component and amount of the sample. That means in HPLC we can easily or very prominently we can determine the qualitative aspect as well as the quantitative aspect of the component present in a mixture. Then configuration of different HPLC, as this is an PPT related to a firm, that is AGN Technology company. So it has many many version of your HPLC. So these are there. I will not go through these things. And what is HPLC used for? That means it is the application part. This is used for the separation of chemical, biological, as well as non-volatile substances or mixtures. If the compound is volatile, example gas, fragrance, hydrocarbon in gasoline, gas chromatography is a better separation technique. If the compound is volatile, typical non-volatile compounds that are to be separated by HPLC are pharmaceutical samples like aspirin, ibuprofen, or acetaminophen, or in short it is Tylenol. Salts like sodium chloride, potassium phosphate, proteins like egg white or blood protein, organic chemicals like polymer, example polystyrene, polyethylene, heavy hydrocarbon like asphalt or motor oil, many natural products like herbal medicine, plant extract, ginseng, thermal unstable compounds such as TNT, enzymes, that is trinitrotoluene, etc. This is what does a liquid chromatograph looks like. This is the chromatogram, which is looks like this. So on the basis of different peaks, we can detect different components present in a mixture. This is component A, component B, and component C. So these are called chromatographic peaks, and each one represents a separate compound. So these are the some pump modules are there, which is not needed from our theoretical point of view. Isocratic pump with same composition, gradient pump with variable mobile phase. We have some discrimination where mobile phase gradient used in. So let's jump to our So it is also an important slide, that is the packing material. This is the stationary phase composition. So this is the porous particles are there with a 5 micron micrometer to 3.5 micrometer on 1.8 micrometer also there. Columns are packed using high pressure to ensure they are stable during use. Most users purchase pre-packed column to use in their liquid chromatograph. These porous particles in the column usually have a chemically bonded phase on their surface which interact with the sample component to be separated from one another. Example, activated charcoal, that is C18, is a popular bonded phase. The process of retention of sample component, that is the retention time already discussed, is the prime thing that is used for separation. Temperature control, detection of HPLC, we have spectroscopic detection, refractive index detection, and fluorescent detection. So spectroscopic detection, we have this one. I think these things are not there in your syllabus. So these are the different particle sizes used in different column. Then we have some mathematical equations are there. Just go through this and try to remember these equations related to your viscosity parameter, specific column resistance, pressure drop is there. These things are there. Then
Excuse
instrumentation.
me, sir.
Yes,
May I ask a question, please?
yes.
Is there any specific difference between HPLC and UFLC?
UFLC.
Yes, sir.
So UFLC,
Ultra high liquid performance chromatography.
ultra fast,
Hanji, sorry, yes.
ultra fast. So high performance and ultra fast means it is depending upon the difference in the flow rate. So when ultra fast in UFHC, your detection time or your separation time is very less than your HPLC, as far as my knowledge is concerned. Actually, I am not in this field of chromatography, my research work, but in UFSC LC, you have faster separation rate than your HPLC, and I think it is more precise also than your HPLC.
All right, thank you.
Okay. So these are the instrumentation part we have in your HPLC. We have some reservoir or the solvent that is the mobile phase is there, with some column is there, analytical column is here, we have the controlling section here. So this is overall the working mechanism or the instrumentation part. Then this is the sample injection unit. We already discussed this one. This is sample in and sample out. So this is the analysis phase. So during this phase, the different components get separated. Then we have the column, what type of material is used and what is the application is there. Everything is written here. Then we have what are the packing material or stationary phases that is generally used. The packing used in modern SPLC consists of small rigid particle having a narrow particle size distribution. The most common packing material used for LCs is prepared from silica or alumina, which is already point out that the packing material is mostly silica or alumina, where silica is acidic and alumina is basic part, synthesized by agglomerating a sub-micron size particle under conditions that lead to larger particle diameter. So generally the packing materials are like this. Then we have silica. This is the size and this is the microporous. Then we have the bonded spherical phase. This is the irregular one in HPLC, and this is the pellicular particle bead. The C is 1 and D is the your porous microparticle. So as the size reduces, the separation becomes more effective, and the pore or the voids interparticular space becomes very less, and the separation is becomes more effective. Just go through these things. What is the particle size and what is the void or interparticulate space is there. These things are written here, and this is again some size exclusion, ion exchange chromatography of the, just see here, this is monolayer, this is dense, this is short, that means this is adsorption. Monolayer adsorption is there, that means this is the surface of the adsorbent on which the adsorbate particles, that is the solute or the different components of the mixture gets adsorbed on the surface of the adsorbent. This forms a cross-linked layer here. This is diluted here. This forms a multi-layer or a long adsorption is there, but it may be the chemical bond may be formed. So this type of mechanisms are there. Then we have adsorption chromatography. So in adsorption chromatography, we have the structure of silica gel. This is the structure of silica gel, or your siloxane bonds are here. Just if I discuss only one unit, let us this silicon. This silicon, we have one OH is bonded to, directly bonded to OH, one with oxygen, another with oxygen also. Okay, so this is a three-dimensional one, and just remember, silicon has the atomic number of 14. That means it has the valence electron of 4. That means it can form maximum of 4 covalent bonds with other element or atoms. So on the basis of this three-dimensional figure is point out here. Then each of these group has different affinity that increases in the following order: they bound siloxane, free siloxane, and hydrogen bonded. So this is hydrogen bonded, and these are bound and free. These are bound type, and this is free. So then we have partition chromatography is there, which is nothing but a liquid chromatography, where the liquid phase is mobile phase is liquid, and the stationary phase is also liquid, but the stationary phase, that is the liquid one, is coated with various supporting stationary phases. So this is organochlorosilane. This is another material which is used in partition chromatography, that is LLC. And here the organochlorosilane is prepared with your silanol with this compound, that is silicon with chloroalkyl, that is trialkyl chloro. Then we have a removal of hydrochloric acid. Then we have the mono unit of this one. Then the same unit is repeated, and we have the loss of water or HCl. I think it is HCl, removal of HCl is there, and we have a cross-link structure like this. So this is your silane, organochlorosilane. Here chlorine is there, organic compound is there, and this is the silane linkage, SiO-Si. This is silane linkage. Then we have sample column packing and mobile phase. This is an example how the polarity and what is the column packing material and what is the mobile phase used for the separation in HPLC. Then ion exchange chromatography is there, already point out that in ion exchange generally ions or ionic compounds get separated, and functional groups like your carboxylic acid or phosphite, these things are generally exchange with anionic species or cationic species, and we have various structural type of ion exchange packaging are there. That is, ion exchange film is there with in inner core, then one active capacity, anion resin bead, then macro ports are there. So these things are used as the stationary phase or the packaging material in ion exchange. Just you have to remember these compounds and how the ion exchange chromatography is applied or used for separation of the different components in a mixture. Here some derivative of ethylene treated with styrene to give this compound, which on react with this one ClCH2O CH3. We have this one, and this is the strong anion exchanger, and this is a weak anion exchanger here. Why this is just see here, this is N plus is here, that is NCH3 whole thrice trimethyl amine, and here just amine is there, NH2. That means here, as the methyl group is three methyl groups are there, the methyl group are regarded as the electron donating group. So as the electron donating becomes more and more, there will be strong anion exchanger will be here. That means electron rich species is this one, and this is relatively electron withdrawing or electron poor species, deficient species. So that's why this is weak anion exchanger. In size exclusion chromatography, we have different sizes of your packaging material. We have the packaging material like styrene, divinyl benzene polymer, of weight 100 to 5000 millions. Just go through these things. Then we have pore size, diameter with operating range. So these include in your size exclusion chromatography under HPLC. So after this, we have property of typical commercial packaging of size exclusion chromatography. So these are some data here. Then ion chromatography is same as your ion exchange, where it is different from ion exchange in the nature of exchange resin. The technique involve an ion exchange column and means of suppressing ion species other than the sample ion to be illuminated in mobile phase to facilitate detection of the sample by a conductivity monitor as schematic illustration. So, so students, let's stop here. That is in unit 8, we have completed size exclusion chromatography. So from tomorrow onwards, we will have discussion on ion chromatography, and we will move forward. And if you have any doubt or any clarification or anything you wish to say, just note down today. We will have discussion tomorrow. So thank you for your patience hearing. And actually, I am very much tired today due to my busy schedule. From 7 a.m. tomorrow to 8 p.m. Night, I am very much very hectic schedule for me for today. So let's stop here. We have 3 days remaining, I think, 31st, 1 and 2. And within 3 days, we have to cover 5 units remaining. So we may make up the syllabus. So don't worry. And we will have the next class tomorrow, most probably at the same time and on the same platform. So thank you to all, and we will have some so Janardhan Iyer or Sheikh Khushwa, if you have something to say or anything to ask, then please ask quickly. Okay, so if no questions are there, then we may wind up this session. So thank you for your patience hearing. So we will meet again. Thank you students.
Thank you, sir.
मीटिंग खत्म। गोभी कैसा है भैया? हाँ, 30 रुपया दे दीजिएगा। 8 बज गए। मिर्चा कैसे? हरा मिर्चा, हरा मिर्चा कैसा है भैया? धनिया, धनिया, हरा मिर्चा कैसे है? हरा मिर्चा, हरा मिर्चा, 100 ग्राम कम हो रहा है, उसी में पिला दिए 100 ग्राम। कैसा है? पैसा कैसा है? एक ही रेट है। हाँ? अरे 400 रुपया। प्याज कैसे? प्याज 30 रुपये। वो कितने रुपया है? 100 ग्राम प्याज दे दीजिए ना। मिर्चा दे दीजिए हरा। और क्या हो गया? आलू तो दे दिया भैया। आलू आलू कैसे है? आलू यही है, वो रेड वाला नहीं है क्या? कैसे है ये? एग्जाम में वो लगल है इंजीनियर का। कितना हो गया आपका? नहीं 15। कौन के कैसे कौन सा 12 है कौन सा 12 आलू भी रखे हैं
आलू ग्रीन लेबल वो भी नहीं, वो भी सही नहीं। हुआ है वो चिकन लगो, नजर मत लगाओ, लाओ यही अंडा तो दूध है, दूध दूध जुला जुला के चल रही है। तो अलग ठंडा को इतना ठंडा मिल जाए, बड़ा ठंडा देश में दे दो, फिर तो और बाबू तो हमको पार्टी दिलवा रहे हैं, क्या कर रहे हैं, क्या तुम हमको बीच लगाए, हमको मुर्गा मिलेगा, सीख कबाब मिलेगा। किया है, सेट किया 3 लाख का, महंगा महंगा जूता होता खरीदा है, खेलने के लिए सर, क्या हुआ है आदमी बहुत शरीफ है, बॉय तो नहीं है यार, बॉय तो तुम ऐसा बोले जैसे ओवर हो गया है यार। ये तो क्या बोलोगे, 88 आदमी को बॉय आप तो कंपेयर करवा दिए, तो बेबी है, राहुल गांधी को बेबी है।
इसका क्या जवाब? हाँ ये डबल कर देना बेटा, कहीं गिर गया तो मुझे देखते रहेंगे, रास्ते में ऑमलेट हो जाएगा। जाकिर से उसकी बहुत दोस्ती है। रेड वाला आलू है। रेड वाला है ना? हाँ प्रपोज किए, जाकिर फट से बोला हाँ बना दिया जाए, बना दिया जाए। जाकिर ने बोला, तो नहीं पता था इन लोगों ने जान पहचान। बोला बिहार को हम नहीं जानते कि जाकिर से उसकी इजी है क्या उलन खींचने वाला? इजी हाँ इजी है उलन वाला, दे दीजिए। 5 वाला है इजी दे यार। सर फैक्चर को 10 वाला दे देंगे। हाँ दो आधा किलो दे दीजिए, और बची दे। ऋण है, ऋण है, रियल रियल नहीं है क्या? रियल है। हाँ डॉग शैम्पू दे दीजिए 10। डॉग नहीं है। शोल्डर को यूज करता नहीं है। सर पैसा नहीं मांगा, फसल का तगड़ा नहीं दे पाएगा। हाँ फसल का तगड़ा चला है। ये ले लो 10 रुपये। अंडा कैसे चला रहा है अभी? अंडा कैसे चल रहा है अभी? काम है 50 का है, 50 नहीं है। इसका जो है ना बहुत ज्यादा गिर जाता है। प्याज कैसे? प्याज 30 रुपया दे दीजिए। 250 500 का देते हैं। 2 रुपया का काफी लग जाएगा। वो फरवरी मार्च में आपको बोला है, फरवरी मार्च में हम कर देंगे। 250 का प्याज नहीं 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 4-5 तारीख तक कर पाएंगे। झूठ नहीं बोलेंगे आप झूठ नहीं बोलेंगे। 4-5 के पहले नहीं हम करेंगे, एक बार 10 नहीं भेजेंगे, ज्यादा ठीक। एक बार बोले ना मुझे जैसे जैसे याद आ रहा है वैसे बोल रहा है याद ठीक है 2 मिनट लगेंगे मुझे 2 मिनट हाँ कस्टमर नहीं है वह जो ले जाता है हमारा हाफ वाले जाता है 45 साइज का है और कुछ ज्यादा सोचे कि ले लो गिर जाएगा फिर कोई फायदा होगा नहीं